Okay. Hi, everyone. My name is Guojun. I'm a PhD student working with Pascal on optimization of machine learning. So this project is going to be kind of theoretical for some of you if you are interested in theory work or the fundamental aspect of machine learning. This project might be fit for you. So today I'm going to talk about EM algorithm and mixture models. So Priyank has talked about mixture of Gaussians, and Pranav have talked about SPNs. So the mixture model is closely related to what they talked about. So first, let's review the basics. So I think you must have know what is unsupervised learning, but let me repeat. So unsupervised learning is to learn the intrinsic representation of unlabeled data. So for example, on the left, we have a cloud of points, and they are not labeled. So we want to group these points into different smaller groups. Like we want to color them into different colors like blue, red, or green. So this can represent, for example, in a bank, we have a profile of customers, and we can represent them in high-dimensional vector, and we want to cluster these customers into different groups. So a mixed model can do that. And so this is called clustering, and there are also other examples of unsupervised learning, such as density estimation or novelty detection. So what is mixture model? So this is a formal definition. So a mixture model is a way to describe a probability distribution, which is a convex combination of conditional distributions. So by convex combination, I mean you have a set of probabilities pi c, and they sum up to 1. So that represents the probability you are in the group C. And in this group, the distribution is described by some PDF fx, which has parameter theta c. So for example, Priyank has talked about mixture of Gaussians. So that is when each function, each conditional distribution is a Gaussian distribution. I think Pascal is going to talk about it in the next lecture. And also, in the discrete case, if you do binary features, so that can be a mixture of Bernoullis. So the conditional distribution is a product of smaller Bernoulli distributions in each direction. So to give you some intuition about these two distributions, so Gaussian in one dimension is like this. And Gaussian in 2 dimensions is like a small hill, and it goes to 0 when xy goes to infinity. So this is a picture for Gaussian. And then for Bernoullis, it's like flipping a coin. So now the variable is binary. It can be either 0 or 1. So if it's 1, then the probability is mu, and if it's 0, then the probability is 1 minus mu. So it's very simple distribution. But even for this simple distribution, like if you study mixture models, there are still a lot of unanswered questions. So for example, in terms of EM. So for any model, like in most models in machine learning, such as neural networks or mixture models, we need to find an objective, like the loss function we want to minimize. So I think you all know maximum likelihood. So we can also translate maximum likelihood to a minimization problem. That's minimizing the negative log likelihood. So you can show that they are equivalent. So how can we minimize this loss function? So there are a variety of algorithms, and they are all called optimization algorithms. So one classic algorithm is called EM, or expectation maximization, which has been there for at least 40 years. So this is just a picture from PRML, the textbook. So first we do the E step. That's to evaluate the posterior distribution. And here the Z is the latent variable. And then we do the M step, where we maximize a Q function, which is an expectation of complete data log likelihood. So if you don't understand the details, that's fine. You can check the book or talk to me. And another optimization algorithm I'm going to talk about is gradient descent, which is very popular in deep learning. Like when we minimize of the loss function in deep learning, we use SGD or ADAM, which are variants of gradient descent. So in gradient descent, first we compute the gradient, and then we take a step. So alpha is the step size or the learning rate, and then we take the opposite direction to the gradient. So this algorithm is kind of simple. So one interesting question in the optimization of mixture model is called the K-cluster region, which we found just recently, maybe this year. So one question is, what if when we want to learn the clusters, what if just some clusters are used? So for example, if the ground truth has 3 clusters, like blue, green, and red, and when we use optimization algorithm to learn this, is that always possible to retrieve the ground truth? Unfortunately, the answer might be no. Like in this case, for example, if you use gradient descent, it might only learn 2 clusters. So we want to understand why. So that leads to a potential project. So again, like if you're really interested in theory and you want to ask how is this learning and like some very fundamental aspect of machine learning, you should try this project. So the project is to study how EM and gradient descent behave in learning mixture models, and can they avoid some bad local minimum, like K-cluster regions I've talked about. And we have some primary results that EM algorithm tends to avoid such bad local minimum. And that's on Bernoulli mixtures, if you still remember. And on Gaussian mixtures, EM can escape these K-cluster regions very fast, like exponentially faster than gradient descent. So our ultimate goal is to understand the convergence properties of these algorithms and their limit, and to propose better algorithms. So that's like in the core of machine learning. Like if you go very deep into machine learning, the theoretical work is the optimization. So you need some mathematical background. Maybe I think you have learned linear algebra, calculus, probability theory, and maybe you have taken some C&O course, continuous optimization, and dynamical systems might be useful but not necessary. So if you are interested in mathematics and doing derivations, formulas, then you should try this project. And here are the references, and thanks for your attention.